This is Strings and Pulley Systems Part 2. In the last video we did a simple string and pulley question without any friction, just to get our heads around the reference frame that we use. Instead of using a plus and minus x-axis and y-axis, we changed our x-axis to a sort of a clockwise, counterclockwise kind of motion that would move the pulley system one way or the other. And then our y-axis remained sort of the same. So we used a plus and a minus for y, but we used a plus to mean clockwise movement of the system in the sort of x-axis, and a minus for counterclockwise movement in the system. So we'll go back to the very same example that we had in the last video, except we'll add in the force of friction. So this time we're just going to make it a little bit different. We're going to add friction in just to see how it changes. So we began with a pulley system that had a block sitting on a tabletop or countertop, and it was a 6 kilogram mass. It was attached by a pulley to a hanging block that was suspended freely, and this was an 8 kilogram block. And we determined the acceleration of this system and the tension in the rope. So our question is still going to be the same. What is the tension in the rope? However, we're going to add friction. What is the tension in the rope? And so to add friction, we simply would indicate that we now are going to have a coefficient of friction in this question. I'll squeeze it over here on the side. Mu is going to equal 0.2. So this extra bit of information now means we have to do a few extra things to figure out the tension in the rope. So we can start by looking at our picture and maybe do a free body diagram and try to figure out what forces we have at play. So we have a gravity force, just like before, Fg. And since we're using the same numbers, these will conveniently come out to numbers that you will remember if you've just watched the previous video. So 8 times 9.8, which is 78.4 newtons of force, pulling downward on the 8 kilogram block. Of course, gravity also pulls on the 6 kilogram block. And I think we use subscripts 8 and Fg6 to keep track of these different gravity forces, because they're not all the same. And we wanted to make sure that we didn't confuse them. Mg, and so this would be 6 times 9.8, which is 58.8 newtons. Then we have to acknowledge that there must be a normal force pushing upwards from the 6 kilogram block, and that would be a normal force. We can tell by looking at it it's probably going to equal the gravity force down, but let's go through the whole solution and work everything out with the numbers so we don't make any assumptions. Now, how will we deal with our new frictional force? Well, we kind of know which way this is going to go because we have done that in the previous question. And you can tell by looking at it, the 8 kilogram block is probably going to pull this whole system this way in a clockwise kind of motion. So that's our x-axis. Our x-axis is all the forces that are lined up along this sort of clockwise versus counterclockwise kind of reference frame. And so since we know that this is going to go this way in a clockwise fashion, then the friction is going to act against that motion. So I can put the frictional force in with confidence on this side, knowing that it's going to act against the motion of the system. So there's my free body diagram. So the first thing I did in the last video was to look at the whole system. Look at the entire system as a whole. So let's do that right here. Let's consider the entire system and see if we can't figure out what's happening. Because remember, these systems are attached by strings, which means they all move together. So if we can figure out the acceleration of the whole system, that acceleration has to be true for every single part of the system, each block within it. So we start by looking for the entire system. And remember our discussion about how the tension, which we never labeled on our picture, but we could put it over here with a little t, knowing there's tension. The tension is irrelevant for the entire system, just like the tiny forces between your molecules are irrelevant when somebody pulls on you with a rope. And so we don't have to worry about the tension at all inside. Think of it as being inside the system. All we need to worry about is what's happening to an entire mass of 14 kilograms, 6 plus 8, all of the mass added together. And if we think about our reference frame that we're talking about, we're going to have an acceleration, or sorry, a force that's causing an acceleration, potentially, this way. I'm drawing it sort of in a clockwise-ish kind of way, because remember, our x-axis is kind of a clockwise, counterclockwise reference frame now. And we've already seen that to be the force of gravity from the 8 kilogram block, which is the 78.4 newtons. It's the force that's over here. That's the only force that is tugging on this system in a clockwise manner. The only other force, then, is the frictional force, which is sort of resisting that tugging in the opposite direction. Now, why don't I need to worry about the other two forces, the normal and the gravity on the 6 kilogram block? Well, the reason is because we are doing a reference frame that has a y-axis that's up and down, and a clockwise-y, counterclockwise-y motion on the other. These two forces, the force of gravity down on the 6 kilogram block, can have no effect on the clockwise or counterclockwise motion of this system. All it can do is pull down on the 6 kilogram block and create a normal force, which is here, which also has no effect on the counterclockwise motion, the sideways motion, this way or this way, of this system. And so we look at these and we realize that they are only y-axis. Okay? Our y-axis is what's happening there. Now we're going to need that information because we know that those two forces will somehow create the frictional force that we have over in our other picture in the entire system, the frictional force right there. So let's quickly examine that and do a sort of Fnet in the y direction. And we're only looking at the 6 kilogram block. And we can see that there is a force of gravity down and there is a normal force going up. Now, as I said, there is no motion, no acceleration up or down on this sort of y-axis. That block is only going to move sideways, isn't it? Which means that its acceleration in the y direction, the up and downy direction, here and here, has got to be 0. And then the gravity force that was acting on it, we saw was 58.8. And it's a downward force. So here I am using a negative to show down. And then the normal force is the force that's up. And we get what we pretty much assumed anyway. The normal force balances the gravity. And so it's equal to 58.8. And that's kind of important because we know we're going to need the normal force when we start figuring out the friction. Now we're going to move back to our clockwise-y, counterclockwise-y reference frame over here for the entire system. So let's do an Fnet. You could call it Fnet X, I suppose, but that makes it a little bit confusing. Let's just call it Fnet, and we understand that we're talking now about the net forces that are in the clockwise, counterclockwise direction. So we won't need to even look at the up and down forces that we just did. This one is kind of out of the picture now, and this one is out of the picture now. So, let's go to our simpler picture. Fnet is simply the frictional force that's trying to pull it one way, and the gravitational force from the 8 kilogram block only that is pulling it the other way. And this time, we're hoping that there's an acceleration, so I'll just put ma here. And the force of friction we know is mu Fn. And of course the force of gravity is mg. And we have enough numbers that we can fill them all in. The mass is the entire system, 14 kilograms. And we want to find out how it's accelerating. The mu was given to us at the start of the question as 0.2, and we have just figured out our normal force of 58 over here, which will then creep over to this side and go into the equation, 58.8. And we also know the m and the g for this. It's this number up here, 78.4. Now, our frictional force, though, is going to the left in our sort of counterclockwise in our new reference frame. So we need to make sure that we put a minus sign there. In fact, I'm going to erase this and make it bigger so that we don't miss it, because it's very important. The minus sign equals negative. Friction is going counterclockwise, or at least it's attempting to move, to prevent the object moving clockwise. So it's in the opposite direction. Now look at this. The gravity force is 78.4. But it's a positive number. Well, how can gravity be positive? It can in this new counterclockwise reference frame. The gravity from the 8 kilogram block is actually making the object move, or the system move, in a clockwise way. And so here's a weird case where we're actually using a positive number to represent gravity. But once you get your head around the reference frame, it's not so odd after all. So it looks like we can do a little bit of calculating here, and we can get ourselves some an answer or a value for this acceleration. If we do 58.8, and we multiply that by 0.2, we can probably do that in our head. It's 11.76 plus 78.4, and again it's a negative 11.76. So if you add those together with 78.4, you're actually doing a little subtraction. It's 66.6 and 14 a on this side. And then we simply divide that by 14, both sides, and we get an A that's equal to 4.76-ish. Remember, we're not using sig figs, so we have to bear in mind that it might not be that precise. Meters per second squared. But that's basically the answer, ballpark. Now it's a positive number. What does that tell us? It tells us that the acceleration is moving in a clockwise sort of fashion. So here on our crazy screen, that's pretty marked up. We can still see, though, on our picture, the big black arrow that I drew originally, way up here, is making this accelerate in a clockwise sort of way. And that makes sense, right? We can tell that the 8 kilogram block is going to pull on the 6 and move it to the side until eventually it falls off the edge of the table and follows the 8 kilogram block to the floor. So now we have the acceleration of the system. Now we can figure out the tension by analyzing any one of the two parts of the system. So what I'm going to do to make things a little clearer is redraw the picture, because the last one is kind of messed up. We have to put a lot of marks on it. So very quickly, here we go, 6 kilograms, and a pulley, and a string, and 8 kilograms, and a coefficient of friction of 0.2, which we've already worked out, so we don't have to sweat that too much. And we can put in our forces, just to remind us, we had an FG for the 8 kilogram block here, and we had an FG for the 6 kilogram block here, and we had a normal force up here. So it's like you were looking at the original picture back again. And we had decided that the friction was going to pull this way. But now we have to focus on our friend tension. We put a little T here, so we have to understand that the tension inside this rope, remember, tension only pulls. Ropes can only pull, they can't push. And so tension occurs in a string in both directions. It pulls this way on the 6 kilogram block, and it also pulls up this way on the 8 kilogram block. And it's the same value, it's the same tension. So what we're going to do is figure out what that tension is. And we're going to do it by analyzing one of the two blocks. Let's take the 8 kilogram block in isolation by itself. If you look at it, the only forces that are affecting it are the force of gravity pulling it down and the tension force pulling it up from the rope. There's no friction here, there's no surface, there's no normal, it's just hanging there. And so we can write a very, very simple Fnet equation to describe this. The net force is the tension plus the gravity pulling it down. And Fnet is equal to ma. And tension here, gravity, mg. So we know that this is an 8 kilogram mass, but here's the catch. The whole system was accelerating at 4.76 in a clockwise sort of direction. Well, that means that every part of the system must be doing the same thing. So that A can go right down here, and we can substitute it into that equation, and so we can put 4.76 right there. And then we have the T, and we've already calculated the gravity force of 8 times 9.8, the mg was 78.4. Now, let's check our signs. The acceleration was in a positive direction because it was clockwise. So forget about up and down anymore. It's just the whole system, clockwise and counterclockwise. So that was positive, and we put a positive number in there, so we're good. We also put 78.4 positive, because even though it looks like it's down, down is not part of our reference frame anymore. It is contributing, remember, to the clockwise motion of the system. So it's also a positive number. Now we're going to multiply 8 times 4.76, and that comes out to about, I'll move down a bit, 38.08. So let's just check that number on the calculator, just so we're safe. Oh, that's not right, is it? It's 38.24. Always double check. 38.24 equals the tension plus the 78.4. So what do? We move the 78.4 over to the other side. It becomes negative 78.4 added to the 38.24, which is the tension. And it looks like the difference is going to be about 40-ish. Well, close enough to 40 anyway. So let's just say it's 40-ish. And it's a negative number. So it's telling us in this case, with respect to the 8 kilogram block, the tension is pulling in a negative direction. Well, does that make sense? Up is negative in our reference frame because an upward force right here in the picture would cause counterclockwise motion, which is a negative in our reference frame. And so that works out. However, when we calculate tension, because it can pull both ways, we are usually only concerned with the magnitude of the tension. So it would be quite correct to say that there is 40 newtons of tension in this rope and not worry about which direction it pulls, because it pulls both ways. Now, if we were to do the very same thing with the other block, we would end up with the very same answer. So just to show you that, let's go through that one too. We could take the other block in isolation, the 6 kilogram block, and I'll just draw him. He sits here on the tabletop, 6 kilograms. He has a force of gravity that's pulling him down, Fg. And it's the force of gravity on the 6 kilogram block. He has a normal force because he is sitting on the surface. And he has a frictional force, which is resisting his motion this way. And he has the tension of the rope, which is in this case pulling sort of to the right in a clockwise-y sort of way. Now, we already have said that the normal force and the gravity force play no particular role whatsoever in the clockwise motion back and forth of this system. They're only important for calculating the friction. So we really don't have to consider them other than to get the normal force, which we already have done. So I'll write those numbers in. We had seen that this was a 58.8 pulling down, which means that our normal force then was 58.8 pulling up. And we have that equation already written, so we don't have to write it again. We did that up here, and we found that out. So we'll just borrow that information and bring it down here. And again, that's only necessary for calculating the friction. So let's look at the net force equation for this particular picture. It would be Fnet, and again, the Fnet in the clockwise, counterclockwise directions. We have force of friction, which is trying to resist the motion, and we have over here our little friend tension. So we have a T, or tension. We know the mass of this object is going to accelerate, and the friction is going to be mu Fn, and we're going to have a tension force. So we just carry that down and put in our numbers. The mass of this block is 6. And again, we know the A because it's the same A from before. The entire system A, which we figured out way up here, 4.76 again. So we bring the 4.76 acceleration down here. If that's the whole system, every piece of the system has to have that same acceleration. Our frictional coefficient was 0.2, and our normal force came from the frictional force, and our Fnet y, which we already calculated, 58.8, so we don't need to worry about that. And then we have our T. Now, the frictional force is again acting in a negative sort of way, so we better make sure we tell the math that that blue arrow is pointing to the left. It's resisting the motion, so we know that. But the tension arrow, well, we're going to find out. The math is going to tell us what sign goes with it. But notice that the acceleration is positive because it was positive before, it still is. So we leave that the way it is. And now we have to do a little bit more of our multiplying here. So we do 6 times 4.74, and that comes out to about 28.44-ish, give or take. And then we do 0.2 times 58.8, which is 11.76, I believe, and it's a negative number plus the tension. And so when we move it to the other side, we get an answer of 28.44 plus 11.76, and you can guess what that's going to equal. Whoops, that's I got my equal sign here messed up. There we go, equals the tension that's left. Well, 28.44 and 11.76 is going to add up to pretty close to 40, isn't it? 40.2-ish or something like that. But that is the same answer for the tension that we got on the other side. So you see, you can use either one, any one. Now notice this one came out to positive 40, whereas the other one came out to negative 40. Well, in this picture, the tension is pulling in a clockwise-y sort of way. And so the math figures that out for us, and it knows that this must be a positive tension. The math is fully comfortable with the fact that ropes and tension pull in both directions. It's only us that have difficulty trying to figure that out. So again, the magnitude is really what matters for tension, and the tension magnitude, whether you do it this way, by looking at the 8 kilogram block, or if you do it this way by looking at the 6 kilogram block, you still get 40 newtons of tension. So that's how we deal with friction. And in the next video, we will add one more little wrinkle where we'll hang a box off of both sides and see how that changes everything.